Hello young physicists, this is our second video on our unit about electric circuits, and it's going to be about circuits themselves. I want you to be able to build a circuit out of just a battery, a light bulb, and a wire, which hopefully you've done already. I want you to be able to draw a schematic of a circuit or a diagram of a circuit, build a circuit from a schematic. These two we'll be working on in labs over the next couple of days. After watching this video, you should be able to explain the difference between a series circuit and a parallel circuit, and also a combo circuit. So you should be able to tell those by just looking at the components or by looking at a schematic. Let's get started. Our ultimate goal in our labs is going to be to use something called a breadboard, which is pictured here, to build circuits. Now the type of circuits that we're going to build are going to be pretty simple, something like what's pictured here, but you can use a breadboard to build a lot of different stuff. So basically a breadboard is like testing a circuit that you want to build before you actually solder or kind of glue with metal all of the parts together. So here's kind of a moderate difficulty breadboarding right here, and this is just crazy stuff happening. So we won't get into something like this, but we'll be doing experiments that are at the very basic level. No matter how complex the circuit you build, all of the circuits have some basic parts. Those parts are the voltage source, which in yesterday's video we said that good voltage sources included batteries or generators. There are going to be connecting wires, like these wires right here, and there's going to be a load. In this case, the load is the light bulb, the thing that's being powered by the circuit. Now what the load is doing is it's actually converting the electric potential energy that's flowing from the battery into another form of energy. So in this case, because of the resistance of the filament in the wire of the light bulb, it's converting electric potential energy into heat and into light. Another thing that we'll find as a part of a circuit will often be a resistor, and we'll look at some pictures of those in just a second. And what resistors are used for is to kind of regulate how much electricity, how much current gets from the battery to the load, from the voltage source to the load. Let's take a closer look at some of these parts, and then we'll look at some circuits. So you have a lot of different electronic devices, and each of those, the reason that you have it is because of the load that's being powered by the voltage source. Here are a few examples. So some simple examples in physics include a motor could be a load that converts electrical potential energy into some type of mechanical energy. A load can be a light that converts electric potential energy into light and heat, or a heating element that converts electricity into heat. So what happens is the load resists current flowing through, and that allows the load to convert the electric potential energy into some other form of energy. So here's a most simple example using a battery to power a light, and here's a switch right in here to when this is down in this position, the light will be lit, but if you move the switch up, then the light will not be lit. Another example of a simple circuit would be the one that's powering this fan, where you have a voltage source, connecting wires, and the load of the fan, and then here's a switch that when you push it down the fan is going to move. Here's another circuit where the voltage source would be the outlet in the wall, and current is passing through these connecting wires, and it's actually going through two loads. So one load is a motor right here, which causes air to blow out of the hairdryer, and another load is this heating element, which makes that air hot. And then there are actually a bunch of switches here, and then that will cause the motor to go faster or slower to blow more or less air, or it might cause the air to be hot or cool. Another part that a lot of circuits have are resistors, and we're going to use resistors in our lab. And what the resistors that we use are going to look like is just like these, where they have a bunch of different color bands on them. But there are a lot of different types of resistors, and here are some shown, like if you open up your computer and look at the circuit board on there, what it will look like. What resistors are used for is to change how much current goes through a wire, and that regulates how much current gets to the load. So for example, with a light bulb, if a lot of current gets to the light bulb will burn brighter, but it will use up the voltage source more quickly. So also, if too much current gets to a light bulb, it could blow the filament on the light bulb and blow the light bulb. So by putting in a resistor, it helps regulate that the right amount of current would get to a light bulb so that it burns bright enough, but not too bright, or doesn't burn itself out. Now, one of the cool things we're going to see about resistors is that they're actually color-coded. And the color coding involves 4 bands, 1, 2, 3, 4, and each of those gives us different pieces of information. And we're going to do a lab about that tomorrow or the next day. So that's a preview of what's to come. In order for a circuit to work, the circuit must be closed. And what that means is it must be like a big circle. So in this case, you can see that everything is connected, and then that way the light bulb is able to light. Obviously you can see those are rays of light or weird looking hair coming from the light bulb. Now when the circuit is open, like here, there's a gap. So here's a gap, and now that circuit is no longer a closed circle. Instead, it's open. And what do you notice? Well, now the light bulb isn't lighting, because electrons will flow out of the battery and through the light bulb into this wire, but they won't be able to connect back to the battery to get charged, like the lift on a roller coaster. So the light bulb won't light. So in order for a circuit to work, it must be closed and it must have no gaps, because the electrons won't be able to jump the gaps. How you can regulate if a circuit is open or closed is to use a switch. Yesterday we talked about how electricity is from the flow of electrons, and I just wanted to kind of fold that into what we're talking about here. So here's our voltage source, our connecting wires, and this one doesn't actually have a load shown on it because the goal of this is just to show you how electrons are flowing. So what happens is the negative end of the battery is the source of electrons, and the electrons flow out of the battery and through the wire, and here you can see them jumping from one copper atom to another and going through this connecting wire back to the positive end of the battery. And now the battery voltage source acts like a lift to get that roller coaster, to get that charge back up to the top so it can make that fall and circuit again. Another cool example is with a light bulb. And when I was a kid, I always noticed that light bulbs, when they burnt out, were kind of like floppy in the middle. And what happened is that filament wire that normally goes through a light bulb and creates light and heat, what happens when a light bulb burns out is that filament wire breaks. And now what happens is there's a gap in the circuit from here to here, and those electrons can't jump anymore. So when a light bulb breaks, actually what's happening is it's breaking the circle of the circuit. The current stops flowing through the light bulb, and you have to replace it. The last thing we want to do with circuits is to be able to draw schematic diagrams. And a schematic diagram of a circuit looks something like this. And there are some basic parts that we're going to look at. So here are the symbols that are represented, that we're going to use to represent different parts of a circuit. This symbol is going to indicate a battery. The smaller end here is going to be the negative side of the battery, and the larger end is going to be the positive side of the battery. So electrons are going to flow this way. A line just represents a wire, connecting wire. One of these jagged lines represents a resistor. A line that looks like this with dots in open, both of these are going to be switches. But this is going to be an open switch that creates a gap and current will not flow through, and this is going to represent a closed switch, where now current can flow through. When you put them all together, it will look something like this. What's missing on here is a load, so let's look at some examples of loads that we're going to use in our labs. The three types of loads that we're going to use in our lab are pictured here. This one is just a regular light bulb, and you can see that it looks like a resistor. The symbol for it looks like a resistor, that squiggly line, but with a circle drawn around it. Another thing we're going to use is called a photocell, or another name for that is like a photoresistor. And you may have seen these before. Here's what it looks like. You may have seen these before, like in a night light or a light sensor. And what happens is if you cover that up and it's dark, like if you could put your thumb over it and it's dark on a night light, that would cause the night light to come on. But if light gets to it, then the night light goes out. We'll play around with those a little bit. Finally, the last type of thing we'll use, the last type of light bulb we'll use is called an LED light bulb. And you see those in all kinds of devices, and we'll talk about what those are a little bit later. But you need to know the symbols. So a photocell or photoresistor has a symbol just like the light bulb, but it has these two arrows on it that I picture as like the light shining on that photoresistor. An LED is represented with this triangle and a line at the end of that triangle, and then arrows going out of it. We'll practice using those in drawing schematics. So here's a schematic diagram with some basic parts. Hopefully you can look at this and say, okay, here's our voltage source, probably a battery. There's the minus end and the plus end. Here's a connecting wire, and that's connected to a switch. In this case, the switch is open, so no current will flow through. That goes to this load, which is a light bulb, the squiggly line with a circle drawn around it. And there's another connecting wire that takes us back to the voltage source to complete the circuit. Here's another example of a schematic. Here we have our voltage source, and from looking at this, you can see that it's kind of a lot of lines, and all that means is that there are kind of like 3 batteries connected to power this circuit. Like, you know how some devices you have to put batteries in and they go in opposite directions? That's kind of what's happening here. So here's the negative part of the battery and the positive part. Electrons would be flowing out this way, and you see here's one light bulb, and then a connecting wire, and then a second light bulb, and a connecting wire, and a third light bulb, and a connecting wire back to the battery. So like this. 3 batteries shown here, connected to 3 light bulbs. Now the way these light bulbs are connected is really important and brings me to our last point, and that's series versus parallel circuits. So the way these light bulbs are connected, this is actually called a series circuit. So let me explain what that means. When loads are connected in series, there's only one path for the electricity to pass through in the circuit. And what happens is the charge passes through each of those parts, kind of one at a time. Think about it as like a single lane road where all of the cars have to drive on the same lane. All right, so if the current is flowing this way, it would have to flow through this light bulb, go up and through the light bulb, then follow this connecting wire and go up and through the other light bulb, then back to the battery. Here's a schematic of that. Sometimes a symbol like this is used for a light bulb, but we're going to use the one with a wavy line and a circle around it. Now another way that things can be connected are through parallel connections. And think about this as like a highway where there's bridges, so there's several paths to complete the circuit. So what happens here is the current flows from the battery through this wire, and it goes through the light and back to the battery. But the pathway could have also gone this way too, and go through this light, and then follow these wires back to the battery. So what does this mean in terms of practicality? Well, let's check it out. So with things connected in series, if one of the bulbs goes out, then both of the bulbs goes out. So here's a bulb that went out. Now what happens is this creates a gap in the circuit. So electrons can't flow in the whole circle. So electrons aren't going to be able to get through this light bulb and back to the battery. So both of these light bulbs are going to go out. Now how that's different in parallel circuits is that if one of the bulbs goes out, the other one is still going to be lit. So this bulb went out and the other one is still lit. And that's because there is still a complete circuit. So charge can still flow through this wire, through this light bulb, and get back to the battery. Here, similarly, charge can flow through and get back to the battery because there are multiple pathways. So this would be like if there was, this situation would be like if there was a road and a big log jam going through the road, and it would block passage through the road. And in this pathway, if there's a log blocking the road, then you can just take the detour, the other pathway, to get to this light. Now there's series circuits, parallel circuits, and there's combo circuits, which is a combination of the two. Let's check out a combo circuit. So here's a schematic of a combo circuit, and let's kind of orient ourselves. So here we're looking at two batteries, the negative end and the positive end. It's a 24-volt battery, and electrons are going to flow out this way. And first they're going to reach these two resistors, R3 and R4. And what you can see here is R3 and R4 are connected in parallel. In other words, the charge can flow this way and still complete the circuit, or the charge can flow this way and still complete the circuit. Then we encounter R1 and R2. And they're also in parallel because we have different ways for the charge to flow, through the R2 pathway or through the R1 pathway. But if you look at it, the reason we have to call this a combo circuit is because the R1, R2 is in series with R3, R4. So, what does this mean? Well, if just R3 burned out, the current could still pass through R4, and R1, R2, and R4 could still be lit. If R2 burnt out, all the rest would still be lit. But if any of these two or these two both burnt out, then they'd all be burnt out. If that's confusing, ask some questions. We're going to be practicing this and looking at it with breadboard circuits. I hope this video was helpful, and I'm really excited about us building some circuits in the next couple days.